All right. Hi, everybody. Welcome to the Question Barn. Where you send my titanium physicist questions and we answer them, and it'll be weekly and pretty fun. This is the first episode. Joining me today is my good friend Jocelyn Reed. Hey, Jocelyn.
Hello.
Everybody remembers Jocelyn. Right. She works on neutron stars and stuff. Okay. So I thought, hey, at the start of every show, why don't we talk about things that are either interesting or annoying? So, Jocelyn, anything interesting or annoying for you this week? Because I have something crazy that I discovered, and it's rocking my world.
Gosh, so it's second week. Oh my gosh, second week of classes, and I just did observing night with my astronomy 101 students. So I'm all keen on telescopes again, and I'm trying to figure out what the heck can you see from Fullerton, California, in the middle of Orange County, which is not a lot because the sky is super bright, but
You take them out onto a hillside with telescopes and
just a field on campus. I mean, we don't have anything fancy. We don't have a permanent setup, so.
Okay, but you bring them like crackers and pop to keep them sated while they look at stars or anything?
Heck no.
You buy them cookies, right?
Heck no. This is for their benefit, dude. They get some extra credit, but
that's pretty fun.
I'm not going to bribe them to come look through telescopes.
Maybe I'll start throwing rocks at my first year class that teach them about ballistic motion.
Science is its own reward, Ben.
Science is its own reward.
I mean, it's awesome. You can see Saturn. Saturn is cool. It looks fake through a telescope if you haven't seen it before.
That sounds pretty good. Saturn is the best thing to look at. I agree. So my favorite thing this week is I discovered this thing called baby metal. So like Japanese idol, like essentially Japanese teenage girl idol groups. There's like 4 or 5 young women dancing and singing, and everything's really, really cutesy.
And super choreographed.
Yeah. So somebody mashed that up with like heavy metal. So there's a group of 3 idols who the band is called Baby Metal, and they dance and sing to like a heavy metal track. So I mean, they're novel songs, like they're not covering songs. So they play their own songs about like eating chocolate and stuff. But then on top of like they're like singing in their high pitched Japanese way. Oh, it's hilarious. So I'm enjoying the hell out of that. It's stupid, but okay. That's it. That's 5 minutes. 5 minutes of small talk. Let's get to the physics. Physics. Okay. So we received a letter from a guy named Russell. Hi, Russell.
Hi, Russell.
It goes like this. Well, I'll read the whole letter and then we'll answer it. Hi, Ben and other high-powered minds of science! ! Comma. I thought that
minds. Sorry. I'm feeling flattered already.
Yeah, well, he included me with all the people who actually have higher-powered minds. I'm honored. Okay, I thought that you might be able to help me with some questions about the speed of light and moving around that speed. First, we know that time dilates as you approach the speed of light, but at what rate? Is it linear, exponential, logarithmic, etc.? As in, does it increase of x kilometers per second have the same increase as 0 kilometers per second as it does at 290,000? Yes.
Have the same effect, not have the same increase. I think that's actually important.
Oh, yeah. Okay. Right. Anyway, moral of the story, you get it. I don't want to read numbers. Nobody's writing the numbers down. Moral of the story is, does the effect change the closer to the speed of light you get? Beta. If someone were traveling at approximately the speed of light and shined a laser behind them, would the distance between the first bit of the laser and the person be increasing at 2 times the speed of light? Neither going faster, just the relative distance between them. Depending on how these come back, I might have more questions. Thanks for all your time in fun physics info, Russell. Okay, hi, Russell. Okay, that was fun. Okay, so 2 questions here. The first question is, we've talked about time dilation before. Does time dilation, how does it work as you approach the speed of light? And secondly, if a person traveling nearly the speed of light shone a light behind them, would they see the light? Would they be informed that the light is receding from them faster than the speed of light?
So I think, well, and the question says, I'm jumping to the second part, but the question says, would the distance between the first bit and the laser the first bit of the laser and the person be increasing at such and such a rate? And of course, since this is relativity, as soon as you say the distance, there is no the distance.
Yeah, that's a good point. I mean, yeah, right. So how can you explain it? Have you ever taught a class on this?
Sort of, yeah. Well, I mean, I've talked about it to people a lot.
Yeah, I've never.
So I think,
yeah. Go on.
Okay, so if I am, person sitting here. Okay, no, let me say this. Okay, to say that someone is traveling at almost the speed of light, you need someone else to be watching them to compare their speed to how they see light travel, right? So if person A just accelerates in an empty universe for infinity time and they're going mind-bogglingly close to the speed of light, but the universe is empty, they just cruise along and they can't tell any difference from themselves just sitting still. So in some sense, there's no universal definition about what it means to be moving close to the speed of light. It depends who's looking at you that you can even say that.
Right, because everybody, regardless of how fast you're traveling, if you're accelerating, the story's slightly different because you can tell if you're accelerating. But
but you stopped accelerating.
Yeah, if
so
you're
now
not
you're
accelerating, you think you're not moving at all. There's various thought experiments where Einstein imagined himself in a closed elevator shaft where he couldn't look out the windows, and he said, in free fall, it's the same as being in space. Me saying that is absolutely meaningless. It's just no wonder I edit the show usually, because, yeah. Did I mention I'm not going to edit this show?
You're not going to edit this show?
I guess I'm going to edit this show a little.
Well, I mean, certainly, I don't mind if you don't edit. It's good to see what rambling we usually do, but it might be a little well, then we should get to the point.
Yeah, okay.
I have to be more robust about getting, or more diligent about getting to the point. Because, okay, so laser question. Let's go back to the laser question. The distance, so if I look at someone and I see they're traveling at the speed of light almost, like 99.9% to the right, and they're shining a laser off to the left, I will certainly see the person and the laser separating at almost twice the speed of light. But person shining the laser still sees the laser separating at exactly the speed of light.
Yeah, so let's say your laser was traveling through, I don't know, some kind of cloud where the person in the spaceship traveling away from his laser could still kind of glean some information. He could see the reflection of the laser as part. Some of the photons of the laser would bounce off and bounce back to him, and he could deduce how fast the laser was traveling away from him. He would do that calculation, and he would say, hey, the laser's traveling at the speed of light.
Yeah,
but
he would see the cloud all squished compared to someone.
Oh, yes, that's right. I mean, there's all sorts of squishing time. Yeah, essentially, he would see a different arrangement of cloud than the person on the ground watching the guy in the rocket ship and the laser separately.
Yeah.
And the moral of the story is everybody's going to tell a slightly different story in order for the one unconquerable truth, which is that the speed of light is constant for everybody.
Yeah, but that means we don't have any distance that you can talk about that everyone will agree on anymore. So it's hard. So hopefully that gets at the second bit of the question. But let's see, the first part of the question, what rate? Well, there's that formula.
Yeah.
I Googled it because I don't have it memorized because I'm a bad relativist.
1 over square root 1 minus v squared over c squared?
Go, Ben, you're a good relativist.
I tattooed that on the inside of my eyelids the day I learned it.
Yeah. But of course that V has to be measured by someone to use that formula. So
that's right. So as we said before, everybody thinks they're at rest. Unless you're accelerating, you can't tell that you're moving at all. So a person in a rocket ship, he's accelerated, he's going... when we say that person in the rocket ship is traveling at nearly the speed of light, that's relative to somebody on the ground, somebody standing on a moon with a telescope somewhere, somebody not moving relative to... The person in the spaceship says, oh, my engines are off. Maybe he can tell how fast he's moving relative to stars outside his ship, but as far as he's concerned, he's not traveling with any speed. His speed might as well be zero. So, to the point. when we say this time dilation effect happens, it's always relative between two different observers. So we say, okay, so we stick one person on the moon. Let's say I stand on the moon, Jocelyn's in the spaceship, okay?
Okay.
Jocelyn, you accelerate. You're relative to me. I see you going almost the speed of light.
Okay, bye.
Okay, see ya. Now, Jocelyn won't feel any time dilation yourself, right?
I mean, yeah. So assume I'm not accelerating, I'm coasting.
Yes.
So I'll see Ben's time dilating.
Right.
Because from what I measure, Ben's moving super fast, so Ben's time has dilated.
Right. But you don't feel any time dilation. You think time's traveling at a regular pace for you. You're not like, whoa, everything's moving slow, right? Time's moving a regular
Even
pace.
though you see me doing that.
So in terms of describing time dilation, it's always relative to me talking about the effect I see Jocelyn. So I look at the clocks on Jocelyn's ship with my giant telescope, and I say, all the clocks are moving super slow on Jocelyn's ship.
But we can't be a little more precise for Russell's question.
Yeah.
Because if I'm zooming past at the speed of light, and then also a turtle floats past like really slowly, you would say, well, that turtle has a pretty like negligible time dilation, and as you see me seem to be moving faster and faster, the time dilation as my speed approaches c, it makes a bigger difference.
Yeah.
And it's in that formula.
Right. So the faster you get, the faster your ship goes. The faster I see your ship going, the slower I see your clocks ticking past. And you're asking for a specific mathematical law. There is an equation you can look up, but the shorthand is it's not exponential. It's faster than exponential. It's an asymptotic approach. So the closer she gets, the closer I see her moving to the speed of light, the slower I see time passing until, if she gets really, 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 really close to the speed of light, I will see her clocks clicking by really, 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 really slowly to the limit where if I could see her moving at the speed of light, time would stop passing for her.
Yes.
And this enters into a bunch of different things. Shortly, a lot of times in physics, people talk about particles that travel at the speed of light. People thought neutrinos traveled at the speed of light. Certainly.
We measure all sorts of cosmic particles coming in at very close to the speed of light.
Yeah, that's right. And the difference between things traveling at the speed of light and things that aren't is that time doesn't pass for things that travel at the speed of light.
So you see that when these cosmic particles last and are stable for longer than you think they should be.
Yeah, that's right. Or even more so, they thought neutrinos traveled at the speed of light, but it turns out that they discovered that neutrinos change their flavor. There's some kind of weird, I would describe it as an internal mechanic, but it's not an internal mechanism inside the neutrino. The neutrino, there's 3 different types of neutrinos, and a neutrino will switch its type. Depending on the laws of quantum mechanics, things are interesting. This comes into the solar neutrino problem, where we were measuring a third too few neutrinos coming from the inside of the sun.
That was a fun. I still wish that we'd been recording when our guest told us the story about when Were we recording when she talked about how she believed that the sun, or someone told her the sun was going to die?
She lived her entire adult life thinking the sun was going out, and then it turns out that it's not, and she found out after 40-some years on our podcast. Yeah.
Titanium physicist, making a difference in people's lives.
That's right. She no longer feared the worst. Well, I mean, if the sun was going out, it still would take millions of years for the signal to propagate out from the center, right? It wouldn't necessarily, even if the nuclear reactions in the middle had stopped, we wouldn't die instantly.
We're fine.
Yeah, no, but we're fine.
It's a problem for, global warming is going to kill everyone before we have to worry about that.
Yeah, we should be worried about global warming. But moral of the story, back to the solar neutrino problem. People thought that neutrinos traveled at the speed of light. In order to travel at the speed of light, things have to have no mass, mathematically. And so people thought that neutrinos had no mass because they're so light they travel almost at the speed of light. They're going really, really fast.
And if they have no mass and they travel at the speed of light, they can't change.
Yeah, that's right. So
because there's no time.
The proof that the solar neutrino problem was resolved because the neutrino was changing their natures as they move through things required that neutrinos have mass. And so the resolution of the solar neutrino problem involved discovering that neutrinos indeed have mass. It's kind of neat because time has to pass for them because they have to change their nature.
Yes.
Yes. So
photons, all those photons that are hitting your eyes, have no internal clock that ticks in any way. They are frozen in their photony states.
Yeah, that's right. In fact, I like to imagine when I was first learning about this, I like to imagine the entire path of one photon. So imagine I was a photon. I might move from here, the surface of the Earth, up past Jupiter, past Neptune, to another star, right, swooping around. It'd be really neat. That entire path, it takes no internal time for me, the photon, to travel along it. So literally, all that path, it's like it's accordion down to one point. Which is weird. It's a weird way to see the universe. General relativity is bonkers.
Yes. It's very hard.
Yeah.
It's very, I mean, that's like, this question is the kind of question that you end up, I catch myself making these kind of assumptions still after working in the field for a decade or more. Because humans are very good at assuming that the thing like distance has a meaning.
Yeah, it's true. Yeah.
And sometimes actually it sort of in practice does.
Distance has a meaning?
Yeah.
Well, I mean,
it's a good enough concept a lot of the time.
I mean, it is, yeah. So there's
even in relativity.
There's something really funny in relativity, which is relativity says there's no absolute motion, right? There's nothing that says, hey, this person is moving. If they're moving at a constant velocity, they think they're still. Somebody else might disagree and say, yeah, you're moving at 5 kilometers an hour, whatever. Everybody will disagree about how fast something's moving in relativity, and that's okay. Within the mathematical framework and philosophical framework, it's okay. Here's the thing, though. The universe does have some preferred motion,
universe time.
Yeah, well, it's like...
rest frame of the universe.
It's like a democratically established zero velocity, because everything in the universe is kind of... everything from the Big Bang. Oh, yes. What you're going to say something...
I was going to be like, so this is one of these things that I lie to my intro astronomy students about.
Yeah.
Because I talk about, like, light was emitted 2,000 years ago from the galaxy, and then the relativist in my head is like, that doesn't make any sense. And then the astrophysicist in my head is like, yes, it does, because the universe defines a rest frame. And
yeah, that's right. So there, we could quite honestly talk about this. That said, if we did, then all of our velocities would be messy because the galaxy is moving we actually, our last show, the galaxy is moving, it's being sucked in by other galaxies, and our sun is moving around the galaxy, and the Earth is moving around the sun, and the Earth is spinning. So if we were just to describe velocities in terms of absolute velocity relative to this universal v is equal to 0, everything would be really, really messy.
Yes, but fortunately, it's all relative, and relative to the things that we are moving and the things we measure, none of this usually makes any difference.
Right.
Except for GPS.
Yep. Okay. Well, yeah, so the corrections come in GPS. There's time. We should probably do a show on GPS sometime soon.
I thought we've talked about GPS corrections.
We have. We've mentioned it over and over and over.
Yeah, because people are like, well, we just like to say, look, relativity actually makes an impact on your life.
That's right. Yeah, time is moving slower when you're in the library.
Well, it depends. It depends what floor the library is on.
I used to have a first year university. No, it was a first year graduate school class, and it was in the top of the building. And I lived in a basement apartment. And so and it was a relativity class. That's an important detail because the joke doesn't make sense otherwise. And so I'd arrive late to my class, and the prof would be like, "Oh, you're 5 minutes late." And I'm like, "Well, I can't help it. Time's traveling at a different rate up here than in my bed. So, what you gonna do?" Yep. Okay, that's probably it for today's show. That was lots of fun, everybody.
Yay!
Yeah, go back to the archives of the Titanium Physicist. We've got lots of interesting explanations. If you like this and other things, you can listen to the show about solar neutrino problems, or the show about the rocket barns, where we talk about special relativity. There's lots of fun things to talk about.
So many relativity shows.
Yes, thank you, Russell, for the love letters. If you want to write your own question in that we might answer, send it in to TIPHYTER, that's TIE Fighter, at titaniumphysics.com. titaniumphysics.com. The email address is on the website. But yeah, TIPHYTER at titaniumphysics.com, and we'll answer your questions. We'll try to do these regularly. They're pretty easy to make. And like I said, I'm not editing it, so,
Well, thanks, Russell. I hope that made sense.
Okay,
Let us
bye.
know if it didn't.
Bye, everybody.
Bye-bye.